Any device that uses heat to perform work. And it's got these features, right? Heat goes in. We have to put energy in. Our device is doing work. So we're putting energy in. That energy is in the form of heat. Comes from a place we call the hot reservoir. Part of the heat does some work. And what's left over is dumped out as exhaust, or excess heat goes to a place we call the cold reservoir. So we like to draw these pictures that look like this. This is what we draw. A hot reservoir, cold reservoir, and our engine. What happens? Heat's flowing, Q hot, comes out of the hot reservoir into the engine. Part of that does work, and part is dumped out as exhaust or as friction. Maybe there's some friction in our engine, and it heats up a little bit, and that heat is lost to the environment. So we always like to use our first law of thermodynamics when we're looking at engines, heat engines. Our first law tells us what goes in has to equal to what comes out, right? Q hot has to equal to the work plus Q cold. It's an energy conservation law. And our efficiency, this is for a heat engine, like the one we looked at a minute ago. It's the work done. It's the desired output. We're trying to do work. So that's the desired output, the work done, divided by what we had to put in to make it happen. And what did we put into the engine? Q hot. So in this case, the work done divided by Q hot is the efficiency of our engine. But I want you to think in terms of desired output divided by what you have to put in to make it happen. Because it changes, right? When we do a refrigerator, it's going to be different. Well, we don't call it efficiency. We call it coefficient of performance. But it's different. For a refrigerator, for an air conditioner, they're all different. But if you just remember the desired output divided by what you put in to make it happen, then they all follow that rule. So you can make some substitutions here. It's the work, in this case, because it's an engine, it's the work divided by Q hot. Work is equal to this, right? That's our first law. It's changed around a little bit. And then you can simplify that a little bit. So we get the efficiency in terms of the heat or the work done, however you like to look at it. Whichever is most useful for the problem. And a French engineer named Carnot said the most efficient heat engine is one that has all reversible processes. So a reversible process, that's kind of a tricky thing to grasp. It means that you can get the system back to where it was. Let me give you an example. When we are on a roller coaster, if there was no friction and no air resistance, the roller coaster takes off, you go through the roller coaster, you get back to your starting point, and you have the same energy that you left with. That would be sort of a reversible process. If there's some friction and air resistance, you go through the roller coaster, you don't quite make it up the last hill back to where you started, right? It has to pull you back up the hill because you've lost a little bit of energy in the process. That's an irreversible process. So Carnot says the most efficient heat engine is one with all reversible processes. Where do you get one of these reversible Carnot heat engines? eBay? No, there's no such thing, right? Every process is irreversible because we always have some losses. We can never quite get 100% reversible process. We have some processes that are pretty close that can approximate it, but there's no way we can make a completely reversible heat engine. So this is the ideal. This is the efficiency of a reversible process, of a Carnot engine. We call that a Carnot engine, one that has all reversible processes. That tells us what the maximum efficiency of the engine is. The interesting thing is that the maximum efficiency is not 100%. You never get out everything you put in. So if I draw it over here, here's my engine. That never happens. We never get out everything we put in, even if this is the highest efficiency, even if it's a Carnot engine with all reversible processes, you never get 100% out. It's always less than that. And what does it tell us? If we can figure out for the Carnot engine what the efficiency is, then that tells us the maximum efficiency possible. And then we can compare our real engines to that, and we can see how close they are to the maximum efficiency that they could be. Does that make sense? We're looking at some ideal, which is not 100%. You might think, well, my ideal is 100%. Everything I put in, I get out. It turns out that's not the case. You can never get this. Carnot said the maximum you can get was with all reversible processes, and it's not 100%. You can figure it out. We'll walk through that. We can figure out what the maximum efficiency is of a Carnot engine, of a maximum efficiency engine. It's never 100%, and that's the benchmark now. That's the benchmark that we would measure our real engines against.